about logarithms. Again, this is also something we start doing in Algebra 2, but today we actually start graphing in Precalc. So I'm going to kind of like go through these and then get to the parts where we can graph, okay? All right. So in the case of logarithms, take a look at these. Here we have the powers of 2, right? 2 to the 1 we know is 2, 2 to the 2 is 4, 2 to the 3 is 8, and so on, right? But what happens in increasing the exponents, right? And in going from exponent of 1, 2 to 3, in going from exponent of 2 to 3, the value increases from 4 all the way to 8, and we skip through all the other numbers. So what if I wanted an exponent that would give me a value of 6, right? So in other words, I'm looking for the exponent so that like 2 to the power of that exponent equals 6. How would I find that? Well, the answer to that is a logarithm, right? So one way of saying 2 to the power of x is equal to 6. Another way of saying the same thing is log base 2 of 6 is equal to x. So if I was walking down the street, right, and there was a billboard and I just saw this on the billboard, I would tell myself, oh my God, somebody is looking for an exponent of 2 that would give them a 6, right? That's how that translates to me, okay? So so then knowing that, we can very easily go back and forth between the logarithmic form in something and the exponential form in something, right? So take a look. We have, when you have a power, you have a base b, an exponent, and then, the value that it equals. So here too, you have a log base b. Y is always the exponent, and then the value that it equals. So since the logarithm is looking for an exponent, the answer to a logarithm is always an exponent. Okay, so whenever I ask you a log blah, blah, blah equals, whatever it equals to, that's the exponent of the base. Okay, so we all know the properties of logarithms, right? So just very, very quickly, look at something like this. Log base b of 1 equals 0. Again, what is the base here? B. I'm looking for the exponent of b that would give me a 1. Well, that's a 0. That's why that's a 0. Here I'm looking for the exponent of b that would give me a b, so that exponent would be 1. What is the exponent of b that would give me b to the x? X. Okay, so it's the same thing. And then, so this is when you have any base, right? However, the common logarithm is when the base is a specific number 10. That's the common base. And so it's so common that we don't have to write it, right? So if I have log base 10 of x, that's just the same as log of x. And if there is no base written here, it's understood that the base is 10. So for example, here I have a hidden base of 10, and now I'm asking what should the exponent of 10 be in order for me to get a 1? Well, that's a 0. What exponent of 10 gives me a 10? A 1, and so on, okay? So let's take a look at how we, knowing that, how we do these then. So here I have a base, and I'm looking for the exponent of 2 that would give me a 16, and that would be 4, okay? Here, sorry. My base is 5, and I want an exponent that would give me 1 over 25. Now, when you have a whole number going to the denominator of a fraction, then we're dealing with negative exponents. So this will be negative 3, okay? I rewrite this as log base 3, 3 to the power of a half, right? Root 3 is 3 to the power of a half. So what should be the exponent of 3 for me to get 3 to the half? Well, that's a half. Oh, what happened there? Oh my gosh. Okay. All right. And then, like, these get so big so quickly, right? 8 to the power of 3 is 512. So this is 3. Um, Normally, like, there'll be numbers on a test that you know. Okay, so here when you have b log b of a number, it's just 15.5. That's also the inverse. Okay, here, 10. Power, this relies on powers of 10, right? So what should be the exponent of 10 to get 10,000? The number of zeros is 4, so it's 4. Okay? Okay, here I have a base of 10, so 10 log 10 of 12 is just 12. This one doesn't rely on any like common base or anything, so we need to just plug that in the calculator, right? Log of 14, this is the only one that's a calculator question. And you all know where the log button is on the calculator, right? So log of 14 is 1.146. We always go to 3 decimal places on these. Okay. Oh, what about for this one? So let's see this. This is log base 16. And I write this as 4 to the power of a third. Okay, now what I want to do, this is a base of 16. I want to write the 4 as a power of 16, right? So how can I do that? Huh? Wait, what? Okay, but I want to do it 16 to the power of 1/2. Do you see that? So I want to write the 4 as 16 to the power of 1/2. I want to make this and this number the same. So what can I do to 16 to get a 4? Raise it to the power of 1/2 to the power of the 1/3. Okay? So now log base 16 and 16 kind of, they don't cancel each other out, but right? So I get 1/2 times a third. Yeah. Okay. Okay. Now, so log base b, common logarithm, the natural logarithm, that's when instead of any other number, you have a base of an e. So you have log base e. And log and e are like soulmates, right? So log base e is called the natural logarithm, and we call it ln. And the reason why it's ln and not nl is because it's French, right? Logarithm naturel. So it's ln, right? So log base e of 7, let's say, it's the same as ln of 7. That's all. There's no mystical thing about ln. It's just log base e. And so all the other properties also apply. So if I have ln, the base is e to the power of 0 would be a 1. E to the 1 is e, and so on. So here, ln of e, what is this? 4.5. And what is this? Oh, what is that? What should be the exponent of e to get a -2? You can't, right? You can't raise anything to an exponent and get a negative number, no positive number. So this is no solution. Whenever the argument here is negative, right, e to the ln of 4 is just 4. And ln of 7, this is also one you put in your calculator, and you get 1.946. Okay? Now, do we remember inverse functions? Right? Let's do a little recap of inverse functions. So, remember when we said if you have a function like this, f of x, the inverse looks like this, right? And what's so special about it? It's symmetric. The two are symmetric around the line y equals x. Yeah? Okay. So, same thing with logarithms. Logarithms are the inverses of exponential functions. So we know what, let's say 2 to the x looks like. right? This is what, let's say, b to the x will look like. And the logarithm log bx looks like this. Do you see how these two are also symmetric or on the line? Y equals x. Yes? Okay, so now what does inverse do? It switches x and y, right? That's the first thing we do. So we switch everything associated with the x to everything associated with the y. The domain becomes the range becomes the domain, vertical asymptotes become horizontal asymptotes, and vice versa. So why don't we go back to when we graphed these lovely exponential functions yesterday, okay? Why don't we take this one, okay? What did we do here? First of all, this has a horizontal asymptote. So when we graph logarithms, we're going to have a vertical asymptote. What's more is when we graph this, we pick points, -1, -0, 1, 2. These were the exponents, correct? Those exponents were graphed on the x-axis, and then the power or the value was graphed on the y-axis, right? So for example, what are the powers of 2? The powers of 2 are 2, 4, 16, and so on and so on. Those were on the y-axis, and then the exponents were here. Exponent of 1, exponent of 2, exponent of 3, and so on, right? So now for logarithms, we're going to switch these. The exponents are going to be graphed here. The powers are going to be graphed here. All right? So let's go back. This time, the exponents are graphed here, and the power is graphed here. So if you take a look, if I erase this, this has a vertical asymptote right here. And so domain and range are switched. Domain goes from 0 to infinity. The range is all real numbers this time. Okay? All right. So, sorry, this is logarithmic growth. And then this is logarithmic decay. All right? Okay. So, for logarithmic growth, graph goes away from the vertical asymptote. Okay? So like that way. All right, so let's go here for a minute. Recall, so we're going to use the inverse powers. All right, so first of all, the asymptote. It's not y equals 0 anymore. Now it's x equals 0. Okay? Now, what is the base here? 2. And what are the powers of 2? So it's 2 to the 0 is 1, and then 2, and then 4, 8. And now if you're going the other way, so 2 to the 1 is 2, and then 4, and then 8, and 16. Now if you're going the other way, 2 to the 0 is 1, then 1/2, 1/4, and so on, right? Those are going to be our values. So now what's going to happen is the exponents are going to be graphed here, and the powers are going to be graphed here. Okay, so it helps to have that insight, and it helps in the beginning to do a little table so you don't get like disoriented because it feels kind of weird. Okay, so oh, sorry. So the exponents are going to go along the y-axis, right? My exponents are going to be -1, 0, 1, 2, and 3. And the powers of 2 are 1/2, 1, 2, 4, 8. Okay? Does that make sense to you guys? Everything is the same as we did before. It's just switched. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2, right? And so now when we graph this, when x is 1/2, y is -1, 1, 0, 2, 1, 4, 2, 8, 3. And so this looks like this. Okay? And if the big deal about exponential functions is that they increase rapidly, the big deal about logarithmic functions is that they increase very, very slowly. Okay? Okay? So when you're coding, right, one thing you always want to look at is like how much memory your code takes up, right? And when you do that, you always want it to be like a logarithmic growth. So like as you put in more and more numbers, you don't want it to take up, too much like processor data. Okay, so what's the domain here? 0 to infinity, range is all real numbers. And we don't have an y-intercept now. We have an x-intercept 1, 0. Okay. End behavior. To the left, okay, we can't go to negative infinity because it doesn't even exist there. So we say as x approaches 0 from the positive side, this is going to negative infinity. And as x approaches infinity, this is going to positive infinity. And it's continuous where? 0 to infinity. Okay? All right, let's do another one. Log base 1/3. So the base is a third, so we're going to go with the powers of a third, right? The asymptote, again, is going to be x equals 0. So, okay, so what are the powers here? I'm going to go from -2. These are going to be my exponents. Okay? So 1/3 to the -2, that's 9, or 3, or 1, 1/3, 1/9. Okay? Yes, Evan. Oh my God. Oh my God. Sorry.
You choose those randomly? Like, because last time you started with -1.
So if it's like decay, I go 1 to the left, right? If it's 1/3 less than 1, then I go that because the numbers get like too big and too small quickly. Yeah, there's no law, and you don't really need this many numbers, Okay. So when x is 9, we're at -2. 3, we're at -1. It's funny, I still like to, like with the logarithms, it feels more right to me to graph from left to right for some reason. Like I get more disoriented otherwise. So this is how it looks. Okay? Questions? Yeah. Okay, so let's move on to the next page. Okay. I have a table here, but when it comes to like an ln, just like graphing the e's, you're gonna have, these are gonna be your calculator questions, right? So for ln, you can use a calculator. However, there is a translation here, right? X minus 6. Where has this graph moved? To the right 6. So what is the asymptote now? X equals 6. Okay? So here it's x equals 6. And then you can use a calculator to graph this one. So, and you can get points from there. So it kind of looks like this. Okay? So the domain now is 6 to infinity. The range is still all real numbers. And then for the end behavior, look, we can't go past 6, right? So the left end behavior is the limit as x approaches 6 from the positive side. So that will be negative infinity and positive infinity. Okay?
So doesn't it give us the asymptote when it asks us for the left?
It does, but I might just ask you what is the end behavior, and then you have to write this whole thing. You know what I mean? Okay. Yeah. Okay. Are you falling asleep? Maybe. I feel much better today than I did yesterday. Yesterday I was like a zombie. Yesterday I was like a zombie and I hadn't even done any partying at all. So I don't know. Okay. Okay. There are lots of places that we use logarithms. For example, in chemistry, pH is a logarithmic scale, right? Yeah. You haven't gotten there yet? Well, it is. Take my word for it. It is. It's my favorite. I love chemistry. I have to say, I should sit in on like chemistry classes. I love chemistry. Okay, moving on. The Richter scale. Also, what does the Richter scale measure? No, earthquakes. What measures rocks?
It starts with R2, sorry.
Oh.
I like that.
So so like for example, if an earthquake has a magnitude of like 1,000, right? I'm sorry. If an earthquake has an intensity of 1,000, you don't want a magnitude of 1,000. If it has an intensity of 1,000, the magnitude will be 3 because it's log base 10. 10 to the power of 3 is 1,000. So there. But now, if another earthquake has an intensity of 10,000, now that's 10 times heavier, right? 10 times more intense. The magnitude goes from 3 to 4. So just because you went up one number on the Richter scale, it doesn't mean, oh, it's like a slight change. No, it's 10 times more. But do you see why it's preferable to use logarithms? Because if you were going to graph 1,000 and 10,000, you need like, graph paper the size of, your height. But if you were going on a logarithm scale, you just go from like 1 to 3 to 4 to 5, right? So that's why it's more beneficial. Another thing that can be modeled using logarithms is the intensity level of a sound. Like, when you say like this is like this many decibels, you know how like your iPhone gives you a warning now if you have like your earbuds in saying like you've been listening at too high of a volume? No? Yeah, you've reached your weekly limit. Yeah. Okay, yeah. I'm usually playing in my car, and so it thinks like I have earbuds. So anyway, yeah. Okay. I have to say, the generation below me is all gonna be hard of hearing after a certain age. I'm not gonna lie. Yeah. Yeah. Well, yes, and then right, because when you get into rock, like there is a minimum, like loudness that you have to right to hear all the drums and stuff, right? Yeah. No. Yeah. Okay. So so the intensity level of a sound is modeled by this. dW is, very simple equation, 10 log blah blah, where W is the intensity of sound in watts per square meter. W naught is the constant watts per square meter. So if the intensity of sound, that's W, okay, of a person talking loudly is this many watts per square meter. So now this is the intensity, right? What is the intensity level of the sound in decibels? So if W is this, what is the intensity level D of W? Okay, and the reason why I like this question is not because of the math involved in there. The reason why I like this question is because all of the quantities basically sound the same. And so it's up to you to keep everything in line, right? And so when you move into calculus where it's 90% word problems, you're going to have to like sift through all of this stuff. So like, yeah, this is DW, which has no, connection to intensity level, right? But you have to keep everything like, organized. All right. So DW is 10 log, and what do we have here? 3.6 times 10 to the negative 8 over 1.0 times 10 to the negative 12. And you know what? Before you reach for your calculators, let's take a look at this for a minute. D of W is equal to 10 log. Let's see if we can make sense of this, right? When you are working with scientific notation, right, you should be able to like compute these things to a certain degree, right? So the numbers compute with the numbers, and then the decimals, the powers with the powers. So 3.6 divided by 1 is 3.6 times. Here, 10 to the negative 8 divided by 10 to the negative 12 is 10 to the power of 4, right? These are things that you should know, right? I mean, it's so much easier to just do that than to be like plugging in all these numbers, making a mistake, blah, 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 right? So now you plug these in. Does anybody have their calculator on them? Go ahead and plug this in. 45.56. Okay, so it's about 46 decibels. Yep. Yeah. Because usually sound is like in whole numbers, right? Decibels. Okay, if the threshold hearing of a certain person with hearing loss is 5 decibels, will a sound with an intensity level of this be audible for that person? So if this is an intensity, right? So how much? So what is this? This is W, right? So let's see. D of W is equal to 10 log 2.1 times 10 to the negative 12 over 1.0 times 10 to the negative 12. These go away, so I'm just left with 10 log 2.1. Can somebody plug that in? 3.22. So can this person hear the sound? No. No, because their threshold is 5 decibels. That means any sound has to be at least 5 decibels or more, so this person can't hear that sound. When I was in college, I had this professor. He had a hearing aid, and it was like remote controlled, and so like when somebody would ask a question from like the very far, like back row of the room, he would have to like pause and like turn up his hearing aid, and then he could hear. And then, anyways, okay, sound in excess of 85 decibels can cause hearing damage. So, okay, that's how your iPhone like regulates all this. Determine the intensity of sound. So intensity is W, right? Always when you have these like confusing letters and stuff, and they're hard to keep track of, always write these down like this. With an intensity level of 85 decibels. So this is now D of W, okay? So 85 is equal to 10 log W over 1 times 10 to the power of 12. Oh, negative 12, thank you. Oh, that would be a whole other thing. So divide by 10 on both sides. 8.5 is equal to log W over 1.0 times 10 to the negative 12. And so now what? Raise it to the power of 10. So remember, this has a base of 10. So this is going to be 10 to the power of 8.5 is equal to this. So again, take a look at this. This is the answer to a logarithm, right? That means it's an exponent. Every exponent needs a base. What's the base? 10. Base to the exponent, 10 to the 5 is equal to this number. So W over 1.0 times 10 to the negative 12. And how much is that? Yeah. So 3.16 times 10 to the negative 4. So we multiply both sides by 1.0 times 10 to the negative 12. Okay, to find W. Okay, what is going to be the unit here? We already had decibels. We're looking for W, remember? Is it watts? Watts per square. Watts is energy, right? So it has to be, or power. So it has to be watts per square meter. Okay? Okay? Yep.
Is the X like it's a multiplication point, right? It's not like a variable.
Oh, yeah. 1 times 10 to the power. I know, right?